Hi, welcome to today's lesson on the electromagnetic spectrum. The question of the day: what do you already know about the electromagnetic spectrum? An electromagnetic wave is a transverse wave where you have oscillating electric and magnetic fields. So it really just means they're like perpendicular to each other. They're kind of coming like this. One is going side to side, one is up and down. You see the blue is functioning in the vertical, and then the red is functioning in the horizontal plane there. So the blue is electric and the red is magnetic, and they work together. So there are um, seven chunks of the electromagnetic spectrum, and we are going to range on one end to a very large wavelength, and then on the other end a very teeny tiny wavelength, and that is how they are classified. So we have radio waves, microwaves, infrared, visible light, ultraviolet, x-ray, and gamma rays. You may have heard about these elsewhere in science, but we are going to go through them um, one by one. But you can see here all of the practical uses of electromagnetic waves. We use them all the time. Radio, TV, Wi-Fi, GPS, remote control, satellites. Visible light just gives the entire world color. So there's a pretty good use for that. Then we have ultraviolet, which is the sun. We get into x-rays, that's perfect for medical imaging, and then we have gamma rays, which can be really, really good for like cancer treatments, but they could also be really, really bad and be like yucky radiation that actually causes cancer. It's kind of weird that a gamma ray can be used for destroying cancer, but it could also be used for like creating cancer. It's interesting how that happens. The electromagnetic waves are all going to move at the same speed, assuming that they are in a vacuum. So the vacuum of space is a good one. But they do move at the speed of light, which we use c, the lowercase c, for light in equations. That's the variable, like E equals mc squared. The c is the speed of light. And that is 3 times 10 to the 8th meters per second, or it is 3 times 10. Oh, I'm sorry. That should have an N. It's 3 times 10 to the 17th nanometers per second. So that's nanometers per second. I apologize. 3 times 10 to the 17th nanometers per second. NM divided by S. Now, these waves can slow down if they are moving through a different medium. Typically, that's going to be something like water or glass. Waves can do some really funny things when they switch mediums. So if you have, you've probably seen it before, just like in your real life, if you have a glass that has a straw in it and you are looking at the straw in water, it'll look like the straw is like broken and detached from itself, right? It'll be like a side by side as opposed to just like a regular straw. That is because the light that you are viewing is sort of being bent as the light goes through the glass and goes through the water. It's going to like distort the image, and that's just because the light is slowing down. And when we do the math, unless it states otherwise, we are going to assume that we're working with the speed of light in a vacuum. Now, radio waves are the biggest of the EM waves. They have the longest wavelength, like kilometers long, and they are the lowest energy part of the electromagnetic spectrum. So, for the most part, these are considered absolutely harmless. Are they actually? Who really knows? But because they are so large, they're very low energy, and they still move quickly because they're moving at the speed of light, but these waves are humongously large, again kilometers long on that wavelength. Then we get into microwaves, and these are a lot shorter. People have opinions on microwaves. I try to avoid mine just because honestly I think food just tastes better not in the microwave, but there are people who have opinions on microwaves. The wavelength here is far shorter than kilometers. I don't know it off the top of my head. I'm sure it's somewhere in here. But what it does is you have this microwave, like a microwave oven. It is going to find molecules and shake them to heat them up. You will learn later in the year when we get to energy and collision theory that heat really is just how fast stuff is moving, sort of. Temperature. The definition of temperature is the average kinetic energy of a sample. So let's just say I have a sample of water and I put a thermometer in it. The thermometer is going to tell me, on average, how quickly the water molecules are moving. If they're moving really fast, I will have a high temperature. If they, on average, are moving slow, I will have a low temperature. So a microwave is going to take those low temperature, slow moving particles and shake them so that they move faster and their temperature climbs. That's really just how a microwave works. But it does that by moving this energy in a wave. Infrared waves are really, really cool. They are mostly related to heat, but you will find them in a remote control. So if you have, I have a remote here. How fantastic. If you have a phone, usually what you can do is pull up your camera. And if you take the end of the remote and you point it at your camera and watch the screen, you can see, I don't know how well you'll be able to see this, but you can see, you see it? It's kind of purplish. You see it blinking? Yeah, that's the infrared signal trying to talk to my TV over there. So you can do that with really like any remote. You can sometimes do it with like video game controllers as they're trying to connect. It really depends, but like a classic remote is going to do it. Go see if you can see it. Because infrared waves cannot be seen to your eyeballs, but your camera will pick it up and translate it for you. So after infrared, our waves are going to get a little bit tinier and we come to visible light. Visible light is the only part of the EM spectrum that we can see without extra tools, and this is what gives the world color. So visible light, when you take all of the colors together, it's just white light. And if you want to split it up into its colors, you can take that beam of white light and put it through a prism, which is really just like a nice shape of glass. And the glass will slow down the light. Remember, I mentioned light can slow when it goes through a new medium. It's going to go through the air. And when it hits the glass, it's going to slow down and it'll split into the rainbow colors. So there are some people who have like these beautiful glass cutouts, basically. They have nice shapes and angles to them, and people will hang them in their windows so that the light will get caught in this pretty glass and split, and then they'll get like rainbows on the wall or on the floor. It's really pretty. So the visible light is, let's look at this. I have this, it's hard to tell that it's blue. This is, okay, this is definitely blue. My whiteout is blue. This is blue because it is absorbing white light. All of the colors are being absorbed except blue is the one that shoots back. So you are able to see that this is blue because the blue light is shooting back at you. This is yellow because all of the white light's being absorbed and yellow is being shot back at you. Emitted would be the proper term. Without light, there is no color. So if you are in the dark, everything's in black and white. Mostly black because it's dark. But the difference between red and orange really is just the wavelength. The difference between orange and yellow, wavelength. Difference between red and purple, wavelength. That's it. They're all considered visible light. They just have different wavelengths. Ultraviolet is those UV rays that are super scary that come from the sun. I love some UV radiation in small amounts every once in a while. I am not part plant, but I like to feel that I'm part plant because I thrive in the sun. I absolutely love it. But too much UV is not good for you. It like cooks your skin. You don't want too much UV. And this is what sunblock helps to shield you from, is from extra too much UV that gives you a sunburn. And it's ultraviolet. Now, something I want to point out, ultraviolet, ultra in science is a prefix for like beyond or extra. It's super purple, if you want to look at it that way. If we go all the way back here, you can see that infrared hits the red end of the rainbow and ultraviolet hits the violet or the purple end of the rainbow. Okay. So that's just a way that I have always used to help me remember what's what. Just in case that helps. But the ultraviolet is a teeny bit smaller than the visible light wavelength. So these waves are getting teenier and teenier and teenier. After ultraviolet comes X-rays. X-rays, really not good for you unless you need them. You should not just be getting X-rays willy-nilly. If you've ever had an X-ray, most people get them at the dentist to look for cavities in your teeth. That's something that would like happen on a regular basis. If you see an orthodontist, they might do like a whole head X-ray to see like where your adult teeth are compared to baby teeth. I mean, at this point, you're probably done with that if you're learning chemistry, but you may have had that happen in the past. When you get an X-ray for your teeth, a lot of the time they put that big heavy apron on you, and if it's a good one, it'll have like the neck protector. Those usually are a big plate of lead. And it's the neck piece is to protect your thyroid, which I will teach you about when you get all the way to nuclear at the end of the year. But this whole thing is to protect parts of your body from the X-rays that don't need the X-rays, because they're not good for you unless you actually need them. But again, this wavelength is itty bitty teeny teeny tiny. The tiniest wavelength of the entire EM spectrum is the gamma rays, and these are the yucky ones that turned Bruce, whatever his name is, into the Hulk. Okay. That's not reality. But you can consider these rays that dangerous. They are super high energy. They have the tiniest wavelength out of everything, and they can penetrate through a foot or two of cement, which is why if you have a really old school building, you may have this symbol on the door, and it says like, this is a nuclear fallout shelter, because it's made of cinder block. If it's mostly like Cold War type stuff. If something bad were to happen, like nuclear weapons wise, the town would all pile into the school to be protected from the gamma radiation. I had this on my middle school. My middle school was a nuclear fallout shelter. So you might see those types of things, but any like prepper bunker situations, it's no good just to go in a basement. You have to have like feet upon feet of cement in order to block these things, because they mean business. They're really bad. But even on this, there is a spectrum between bad and worse, more or less, and also the amount that's pouring out. So back when you were learning Rutherford, he was moving alpha particles, which is a high energy form of radiation, and he was shooting them at the gold foil, right? Because he was working with a small amount of, I want to say it was francium inside his lead box with the pinhole. He's working with a small amount of it, and it was in a lead box. The exposure was very minimal. If you like are digging in your backyard and find uranium, it's just pouring out in all directions. Depending on the amount that's there, you could have a lot of radiation. You won't find uranium in your backyard. But even so, the amount in one way or the other can vary. So that is the electromagnetic spectrum. 7 parts. They are moving at the speed of light, which is 3 times 10 to the 8th meters per second, or 3 times 10 to the 17th nanometers per second. Apologies. I will make sure that is fixed. So if your teacher is using this in real life, it probably says nanometers. And this is their speed based on them being in a vacuum. They can slow down when they are forced to move through a medium at all. And the difference between them is their wavelength, more or less. All right, if there's any questions, feel free to leave them in the comment section below the video. Subscribe so you don't miss the next lesson, and I'll see you there. Bye.